Hello, and thank you for joining us. I am Jasmine Navarez, Digital Content Coordinator at Simulations Plus. I'll be hosting today's webinar behind the scenes, making sure we don't have any technical difficulties. In this webinar, Neil Miller, Vice President of Product, and Xavier Pepin, Vice President of PBPK and R&D, will discuss how the P-PSD module integrates drug product batch dissolution data into PBBM and provides recommendations on optimization and validation. Business Development Director Heather Squire will serve as our moderator today. A few housekeeping items before we begin. We take your privacy rights seriously by registering for and attending this event or participating in the Q&A session. You are providing consent for us to contact you for follow-up. You may ask questions via the questions panel on your dashboard at any time. If you need assistance, please use the hand raise icon. We'll address all questions in the Q&A after the presentation. And I'll go ahead and pass things over to Heather to introduce our speakers.
Thank you, Jasmine. Hi, everyone. Heather Squire, Business Director for Simulations Plus. I'm pleased to introduce both Neil Miller and Xavier Pepin. Neil is a DMPK scientist by training who founded a passion for PBPK modeling while working at GSK and in the pharmaceutical industry for over 20 years. He loved GastroPlus so much that he joined Simulations Plus and is now the project manager for us. So we're very grateful to have Neil with us, as well as Xavier. Xavier is a pharmacist and formulator by trade. He has over 25 years of experience in the pharmaceutical industry and 15 years in biopharmaceuticals. He joined Simulations Plus 3 years ago and is the Vice President of PBPK and R&D. He's published over 60 papers in the field of surface energy, formulation technology, and biopharmaceuticals. Take it away.
All right, thanks, Heather, and for the nice introduction. So good morning, good afternoon, everyone. I'm very pleased today to talk about P-PSD and how we can use it to enable the in vivo dissolution prediction of drug products. I have a few slides for introduction, and then we'll move to a live demo. So the objectives of today's training is to learn a bit more about P-PSD and how it compares to other modeling approaches, and we will mainly do this through a live demo. Through this live demo, I'll show you how to fit and use the P-PSD, and then we will do a quick comparison of the Z factor and the P-PSD on a real case study, and we'll finish with some Q&A. So the basic concept behind the P-PSD is how we model dissolution, and you're all probably familiar with the Noyce-Whitney equation, which looks at the mass of solid disappearing as a function of time, which is related to the surface area available for dissolution, the diffusion coefficient of the drug, the thickness of the unstored water layer, and the concentration difference between what happens at the surface, so the drug solubility, and the concentration building in the bulk of the solution. So the concept here introduces H, which is the thickness of the unstored water layer surrounding a solid particle, and the bulk is defined at the end of H, going from the solid surface towards the bulk. At the beginning of dissolution, you have zero concentration. As you build up concentration of drug, you may reach saturation, so your concentration could stop the dissolution from happening. So the P-PSD is really about how we represent the surface area, which changes with time. Ideally, we would like to measure it, but it's really hard to measure drug substance surface area within a drug product, especially for a solid oral dosage form. And the reasons behind is, first of all, the techniques for measuring surface area of a drug substance are not adapted to the shape of the particles, which really are far away from spherical. Particles can be aggregated. Those aggregates can resist or not the technique of laser diffraction, for example. So whether we use a wet method or a dry method, there's lots of caveats to relying only on a laser diffraction to measure surface area. And then, of course, your drug substance is just an intermediate of your product, because you will You will put some excipients, you will do manufacturing, which may change as well the surface area of your product. In the end, what you have is a product that you give to patients, and this is what you should characterize, and that's where you should look at the surface area of the drug substance. So in order to characterize that surface area, there are different methods. The first two here, the direct input and the viable fit, are not mechanistic, and I will not talk about this today. But we will focus on mechanistic methods for fitting dissolution. So your product batches, you can either use a Z factor or the P-PSD approach. And I will demo the two, mostly the P-PSD, but we'll compare it to the Z factor. Normally, the Z factor should not depend on pH of your solution, but if it does, you have to find the reason and justify the use of the Z factor versus pH, which is another option within GastroPlus. And it could be, for example, because your excipient is have pH dependent wettability or dissolution, for example. So just briefly to remind ourselves what the Z factor is, it's composite parameter, which is a unique bin, so a unique, it doesn't vary, it's a unique parameter, which represents the diffusion coefficient of your drug, the thickness of the unstretched water layer, the true density of your crystal, and the initial drug particle radius. So that usually typically fits well the initial part of the dissolution. If you have more complex dissolution like biphasic dissolution, it may not fit perfectly well, but that's the Z in a nutshell. With the P-PSD, it's slightly different. So we are, of course, going to have some bins of particles, which will have a certain mass of drug associated to each bin. And each of those bins are treated individually and as a group for handling the surface area as a function of time. The full equation is here. I'll come back to the equation in a minute, but basically you differentiate between unbound drug flux and bound drug flux, and accounting for different thicknesses of the unstretched water layer depending on what diffuses, sorry, in your medium, if it's a big micelle or a small molecule. This is, I won't spend too much time on this, but some people may be interested in the math behind. So just to show the filiation of these equations, the main assumption behind the P-PSD is that the micelles will diffuse faster than the drug, and or will diffuse, sorry, as fast as the drug, quite fast, and may reduce the unbound drug flux because of the redissolution at the surface. That's the main assumption. But other than this, or what I've already mentioned, the different thicknesses, different diffusion coefficient for bound drug and unbound drug, it's very classical equation, and it's coming from the Gamsey's paper back in 2010, which did not differentiate for a different thickness of boundary layer. So that's all I have. Yeah, the last slide I think is really important, and we will illustrate it with the demo, is the importance of choosing the right data for fitting your P-PSD. You need to have the best discrimination, so to favor a profile in your dissolution data. And to have the best discrimination, you can look at this straight line starting from 0 times 0, 0% dissolved, to the end of the experiment, 100% dissolved. If your points are near that virtual red line here, it means you have probably the best discrimination, and that's the method you should use. So with this, I will move to the live demo. So the example I've chosen today is acalabrutinib. So this is a weak base with very low solubility, very low intrinsic solubility, 2 basic pKa's, and 1 acidic pKa, which is not going to play any role in the physiological pH range. But there is a big impact of pH on dissolution, and we will use that as an example to show the simulations in the fastest state or when we give a PPI. So in terms of P-PSD fitting, of course, you need dissolution data. So you will go to the observed data and select in vitro dissolution release. And here you have, you can create batches. So I have created here 4 different batches of product. And for this particular batch that we will treat for the P-PSD, I've already created some dissolution data, but I'm going to just demonstrate how to integrate dissolution. So if you create your batch, you can add a new measurement. So I'm going to add an extra measurement. Hope you guys can still hear me. And for that extra measurement, the first thing you need to do is to make sure the units are aligned with your raw data. So I have here my inputs, and I'm going to take my data here just to show you, to illustrate. I've got % dissolved as a function of time in minutes. So I need to align my time unit to minutes, and I need to do it before pasting the information in. Otherwise, you end up with hours, and that can lead to significant differences. Always check that your data makes sense. You know, when you have the you have pasted your data, look at the time unit and scale if it makes sense or not, and then you can if it doesn't, you can just select the what you've entered and delete what you've just entered and redo it. If you change the unit again, it will keep the hours if you put the hours, so that will create a problem. Once you've integrated your data, if you scroll down, you have this panel here. You're probably familiar with it. You can enter the dose in milligram, the volume, the pH, and the solubility, and we will use that for the Z factor fitting, for example. So once you've, for that particular batch, once you've entered the observed data, you can then move to the P-PSD module, which is on the right. And here we have 3 panels. So the first thing you will see is those 3 panels. So surfactant, you can create a surfactant if it's not in the list of predefined surfactant. In the inputs, you will collect your dissolution data, and we will do this for this new batch. So let me do it for you. So you click on add, and you're going to create this batch. So it's always good to have a piece of paper or to navigate to your Excel file. But let me just write it quickly. So I suggest you use as an input this batch name and the pH maybe, or just a unique identifier of your mediums. So I'm going to use pH. And the good thing about GastroPlus is you can do some batch work. So I'm just going to select this text, and I've just hit Control-C just to copy it. So I'm going to create pH 2. I'm going to create pH 2.5. And pH 3, where it's quite easy to create different inputs. One is passive. So once you've created your inputs, you need to link. So this is just a name I've put in a table. I need to link it to the actual raw data. So if you look at all those lines, I need to select my group name for this particular batch and the right series. So this is I've now linked it to the right dissolution data, and I have to do it for all of them. So 2.5. So I don't know how you will end up working in this module, but I like to do things in batches. So I just go from the left to right and then top down, so I don't miss anything. But that's, I think, a preference. You could do line by line, but that's not how it chose to work. But that's a pretty, I would say, personal choice. Right. So now I've linked all my raw data. So I have my names correspond to the raw data. I still need to indicate the right formulation here. So I'm just going to select the right formulation. All right, it's probably the most difficult part is done now. So now we've done this. We've linked the inputs to the raw data and the formulation name. So if you scroll down, you can now start to indicate some input parameters. So for example, here are the details. Since I've created an input with a surfactant, I need to indicate which surfactant I'm using. So it's FASIF V1. You can put the concentration, the affinity to the micelle, and I can show you in the later on how to fit that data separately. You need to indicate the aqueous surface solubility, which is for this particular experiment, this value here, and the total apparent solubility is calculated automatically. That's 120 milligram per liter. So that's correct. Then for the other experiments, quickly, you just need, because they didn't use any surfactant, you just need to put the aqueous solubility. So be careful with the units. It's all in milligram per liter. So that's the only thing you should remember. Page 3 is page 4, 5. 6.8. And that's it. I've done all my batch here. So once you fill in the information, you can now click on this button here called Calculate Sync Values. And for each formulation, so we're going to focus on this batch W026394. You can see each of the experiments were ranked. So there's a calculation of the sync value and the predicted maximum percent dissolved, and the software will suggest an experiment for the optimization of the P-PSD and the rest for the validation. So here the suggestion is to use FASIF. But if you remember well my dissolution data, in FASIF, I have incomplete dissolution. So the 100% dissolved is a theoretical 100% dissolution based on the solubility of 120 milligram per liter, because we use 900 milliliter for the experiment, and because I only dosed 100 milligram for the dissolution, theoretically I should be able to dissolve everything, and this is the lowest sync. That's why the software picked that experiment. But instead of picking the FASIF, I'm going to take the pH3, because pH3, which is here, you can see the green highlight, it goes to 100%, and this is also giving me the nicest profile out of the other experiments. So I'm going to pick pH3 and not FASIF. And this is speaking to the last slide I was showing you on making sure you pick the right dissolution data for your fitting. So going back to the P-PSD, now we have created all these details. We can create a run. So you click on run. So this panel opens up, and you can click on add. So best thing probably is just to keep that batch number, and you can say P-PSD at the end, or just keep the batch number. You need to select the right formulation, and then you need to indicate which kind of precision you want for the fitting. And I would suggest you keep 10% initially, and then you can always go back, click on fitting again, and select a lower precision to get a closer fit to your data. So once you've created a run, indicated the drug formulation, you can click on fitting. So here you've got all your inputs that we've created. So I said we would use the pH3, and we can click on fit. So you don't need to indicate any starting radius or any mass. If you want to indicate starting radius or change it during the course of the fitting, you can of course do that. And you can reduce the tolerance and redo this process. So this is the first result. I have an AFE of 1.06, so about 6% error in my fitting, which is not too bad. I can immediately check how this P-PSD fares. So if you click on the last panel, which is called validation, you could select the experiments, click on validate, and have a look at do predictions. So it's a mixed bag, really. There are some experiments here, pH 6.8, which is clearly under-predicted with an AFE of 0.5, so it's not good. I'm not doing a good job throughout the pH range. So let's go back and change that. So there's the initial, let's say, fitting was done with 10%, so we could reduce this to 5, or we could also fit across two different experiments. So my choice today would be to select two experiments as an input and then do not change the precision and click on fit again. So here I'm asking the software to fit both the pH 3 and the pH 6.8, and the average AFE should be less than 10%. That's what I'm asking the software to do. So it could take a little bit longer because you are going to optimize against two dissolution rates, but that's still quite fast compared to what you would do manually. So here we go. These are so basically there's a message there on top saying there's no P-PSD that can explain all the dissolution data within 10%. So he couldn't find, if you look at the average of the two AFEs, he couldn't find something that would the average would be less than 10%. So you can acknowledge that message, and indeed, if you look at the data, you see that we are kind of overshooting here a little bit, and then initially for the pH 3, and then under predicting, over predicting. So it's not good. We need to change that. So at this point, because it didn't even succeed with the 10% precision error, I would add another bin to help him. So you can pick whatever you want. You can pick 100, 50, or anything. You can put any mass fraction you want. They're both around 0.5, so I'm going to give equal chance to the third bin, and I'm going to click on fit again. So here, there's no message, but look at the data. We are doing a better job with pH 3, but still over predicting pH 6.8. So let's reduce this to the prediction error to 5% and click again. So what I'm trying to illustrate to you is that this is not going to give you immediately the solution you want. You have to do some back and forth with the with the software. You have to do the validation to check that you can do a good prediction across your dissolution data. And this, I mean, you have to make a decision on this, but ultimately the judge of peace, I would say, will be how well you predict your in vivo PK, and we will see this in a minute. So I'm letting it work. So the more complicated your number of bins, the more experiments you select for your fitting, the longer it will take. But eventually you could do a good job. So now I've got very good prediction for the pH 3, less than 2% error, and I'm less than 10% for the pH 6.8. So that, through my own interpretation of those AAFE results, is that I'm doing a good job for both dissolution methods. So I can check with the validation now. And if we look across the board, there is a little bit of under prediction for FASIF. All the rests are less than 20%, apart from pH 4.5, but from experimental discussion with the analyst, there is something funky about that pH 4.5 data, so this can be disregarded. I think at this stage you need to have a discussion with your analyst, and I'm sorry there was no analyst today for this webinar, but if you meet them, if you meet your colleagues, you can talk to them, and you can discuss this with them, because you have to weigh in the trust you have in your input data. But over the rest of them, in between pH 2 and pH 6.8, we're doing a good job, less than 20% error. So let's transfer that P-PSD. So we're happy with that. Click on transfer here. You can acknowledge the transfer. And when you go back to your observed data, if you go to the particle size distribution, you can see now there is a new group name, which is here, which is the P-PSD that was fitted in the run. So that's sorry, if we go back up, you have now 4 bins, and they're been transferred to this table here, so they can be used as an input and observed data. So how do we now link this P-PSD to the specific batch? Well, it's very easy. You go to the compounds tab, dosing tab. You select your formulation. So here this capsule batch, and under particle size and forms, you will select tabulated as an input, and take the P-PSD here that you've just extracted. So this is this particular batch there. I would suggest you save your product at this stage, so to keep all this, to make sure that all these changes have been saved. And once you've saved the project, you can run the simulation. So if I select this particular study, which used that batch, so if you go to the dosing schedule, the study 113 used this particular batch that we just fitted the P-PSD for. Okay, it works now. So that's the results for that simulation. So quite good. I'm just gonna extract the information here and copy the results to our presentation. So let's just go here, insert a new slide, and paste it. Right, so this is with the P-PSD. Now we're going to do the same thing with the Z factor. So if you go to the simulation and under compound setting, if you navigate to your dissolution model, you can switch from Johnson model to the Z factor. So here we retrieve that table that we have filled, if you remember, with all the observed data and the solubilities. And if you scroll down a bit, you can solve the Z factor across all this data. And I'll accept the fit. And now I can run the simulation. And this is the simulation. So not too bad either. If I now extract that information and paste it in PowerPoint. So overall, very close predictions, as you can see here. The Cmax, however, is slightly higher for the Z factor, which is on the right, versus the P-PSD. So if you want to calculate quickly the errors, you'll find 5% roughly over prediction of Cmax and 11% over prediction of Cmax for the Z factor. So the P-PSD is a little bit better in terms of prediction accuracy for the Cmax, but overall it's still within the clinical variability. So I wouldn't say one method is necessarily better than the other, but P-PSD is doing a slightly better job for that particular batch. Now, what I want to show you as well is another simulation with another batch of products. So this particular batch, if I just show you the data for dissolution, is batch NVTF. So this was an early batch, phase 1 batch, which is not the commercial formulation, which dissolved rapidly initially and then had a very slow dissolution in pH 1. And so the solubility of that drug in pH 1 is quite high. It's 18.2 mg per ml. And I will show you how the P-PSD and the Z factor compare for that particular batch. So if we start a simulation first with the P-PSD. So there were two arms for that study. The fasted state, which was so with an acidic stomach pH, and the PPI as well. So I'm just showing you what the P-PSD gives you for both these simulations, the PPI, and if I overlay the fasted and change the color of the simulation so you can see something, you will see there is a quite a big difference between the exposure in the fasted state or with PPI, and that's related to the free base liability, or let's say pH dependence with the stomach in the pH in the stomach. So overall, good predictions. I'm just going to copy this and paste it in the new slide. I need a new slide. All right, so that's on the left, the P-PSD. You may be interested in how I fitted the PPI. So it's exactly the same, but you just change the physiology. So you go to your physiologies, and in the GI tract, you change the pH in the stomach. Here I selected 5.5, which is roughly an average, slightly higher level for the PPI. And of course, the physiology for the fasted state is the same human, but pH 1.3 and the default pH in the stomach. Now, if we do the same simulations, but instead of using the P-PSD, we're going to use the Z factor. So coming back to the fasted state, I'm switching to the Z factor, and here there's only one data, exactly the same data, but we're going to fit the Z factor. So I'm going to solve that and accept the fit, and then run the simulation. So fasted state, there is absorption, but it's not as good. For the simulation with PPI, so PPI is here. Again, switching to the Z factor, it's the same Z factor, so I'm using the same Z factor, and I just run the simulation. And that's the simulation for the PPI with the Z factor. So if I overlay the two and extract the information, color by simulation, you can now see we're doing a very bad job for the PPI, and not so good a job for the fasted state either. So the Z factor has failed to predict the PK for that drug in with PPI, and that's because the drug dissolution is atypical. I would say it's not like a first order dissolution. So here, clear difference between the two for that particular formulation. So the bottom line message is that maybe the Z factor will work well across for certain formulations, but not for others, and that depends really on how your formulation dissolves. The P-PSD clearly has an advantage when the dissolution is biphasic or multiphasic, because the Z factor is just a unique term. It doesn't change. I mean, it's not granular enough. And so it cannot capture very well dissolution that goes fast and then slow. That's the bottom line message. And with this, maybe I went really fast, but with this, I would like to thank you for your attention, and we can take some questions.
And thank you, Xavier. That was a great example of the value of the PPSD approach, as well as showing off the functionalities in the latest version of GastroPlus for the plotting. The ability to look at multiple simulations and the way that you put the results on the plot. And if you'd had time, I'm sure you would have colored those to link those with the plots as well. So that there's a lot in GastroPlus 10.2 for our users. But we've had some questions today about the PPSD. The first one I think you've partially answered, but we'll circle back to it. It's how do you optimize the number of bins in the PPSD approach?
Yes, that's an excellent question. Ideally, and I can go back to the PPSD module. Ideally, you would want to minimize it to well represent your dissolution without adding too many bins. So it's really a question of where do you stop? And the way the software has been built is that when you use it with starting from no bins, so when you start to run, you can really the first fitting exercise you would do is with no bins, so you can remove them completely. And if you when you start, you have an empty grid here. So the software will try with one bin. If it cannot find a solution with one bin, it will propose two bins, etc. So it's just a gradual increasing the number of bins. And of course, you need to set yourself with predefined precision tolerance. So I would say you start with 10, you move to 5. If you have predictions below 5, you stop and you verify against additional data, supplementary data if you have them. If not, I would stop at 5. If you get less than 5% prediction, it's probably very good already. And that will give you maybe 2 bins, maybe 3 bins, maybe just 1 bin. It really depends on how close is your dissolution from an ideal first order dissolution, really. It's so for example, for this particular batch, it's very far from first order because it starts really fast and then slows down. And that's why we needed 3 bins to capture it, or 2 bins at minimum.
Thank you. And in the past, I think we've had a question of what's the maximum number of bins. I believe it's 10.
So 10, yes. Yeah, you can go up to 10. I wouldn't advise going up to 10. But sometimes you'll have 5. In the example we just did, we had 5, I think, 4 or 5. So it's really up to you and the software, not just 4, to decide on that number of bins. And for example, if you end up with 2 bins really close to one another, you could merge the mass fraction, simplify it, so you can you can round them up, you can manipulate them after the software has done the fitting, and to make sure you have the minimum number of bins. You can always verify it, so you don't click fit again. For example, if I had 63 and 64, I would probably take one of them, just sum up the mass, and then straight away, so you can delete one line. For example, here you select the line, you click on delete row, and that would remove that row, and then you could sum up the mass and then just do validation again. So you don't click on fit, you click on validate again. And if you're happy with that new validation, you just transfer again. So if you keep clicking on transfer, it will create a new observed data, and then you can decide depending on. So if you had, for example, multiple P-PSDs here for a specific batch. So for example, here I had one already. I have a second one that I just did with you. If you do a third example or third fitting, you could keep them and then test them against the PK profiles and then select the one you want. So that's more of a top-down approach. But the bottom-up approach I've just demonstrated you works well. And I did before we had this webinar, I did multiple fittings, because sometimes you don't exactly arrive at the same solution for the P-PSD, and I compared them. And you do have some differences. So for example, I run multiple P-PSDs for the same batch here, and when you look at the Cmax predictions, they're not exactly. So that one is the one on the right is this one is the I think this one is the Z factor, but the other ones were from the P-PSD. So it's there, you will get some slight variations, and you're sometimes slightly closer to the Cmax, sometimes higher, but it's overall within 4 to 7%. This one is 11% error. That's the Z factor that we did together as well. So I guess from the other message here is that even if you don't have exactly the same value, you could still do a good prediction, because overall you're fitting your in vitro data, and you can translate the in vitro data to in vivo situation in the fasted state or without PPI, and that's the beauty of that translation. You've got more granularity than the Z factor, which is only one parameter, but it's basically the same principle. It's a mechanistic model, and you can predict in vivo PK and in vivo dissolution.
So in this example here, there's a fair amount of data, certainly in terms of dissolution profiles. One question we've had is, what's the minimum amount of data that you would need to use one?
If you're sure about the inputs, so for that batch NVTF, we didn't have a choice, because that was the QC method at the time, and there was only one dissolution rate that was ever measured. So that's it. You just have pH 1, and you have to work with it. And from what I've shown you, the prediction of PK is quite good when you apply the right method for dissolution fitting. So sometimes just one method is enough, but of course, if you've got other batches on which you've demonstrated the validation part of the P-PSD, which is clearly embedded in the module. So that validation part, of course, if you only have one profile, you can't do the validation because it's going to be very good, of course, on the predictions. But that's something you can work out maybe with technical batch. If you have side batches, then you can do that validation on a different batch, just showing that it does work across different pH.
And obviously, as the new data comes in, you would add it to the project, and then it would be stored in the PPSD, and you can include that new data. So you can kind of build as the project evolves and the data grows, the data set grows for that particular compound or that formulation.
Yeah.
Thank you. So the next question is, could you please show how to create a new surfactant?
Sure. So you would go to the top of the PPSD and just click on Add. So you select a name and a molecular weight. That's it. You just now click on Save. Oops, sorry. And then you can use it to basically indicate your CMCs.
We've had a question in, is the example that you've just shown available in the GastroPlus manual? I can answer that and say I don't think it is. So I guess, are we able to share this example with people if they're interested?
I will have to look in what was published. I think that one was published, so yes, we could probably share it. Yeah.
Thank you. We've then got a question around just checking the time. So we'll take a couple more questions, and those that we don't get to answer today, we will follow up. So how can we use the PPSD module for nanoparticles? Do we have an example for that?
We don't have an example for that, but you could, in theory, use it for nanoparticles. If you have, I would say, sufficient granularity, so you would need probably specific technique to measure the dissolution rate of nanoparticles, because you need to have some points. You need to have some points between 0 and 100% to be able to fit something. But at this, if you do have nanoparticles as a solid form in a solid dosage form, yes, then I would recommend you do use the PPSD. If you have nanoparticles as suspension, I would recommend you use laser diffraction and use that as an input directly, so you can use your observed data and create a particle size distribution straight away from your laser. Because if it's a suspension, you're probably better off using laser diffraction. Solid dosage form is probably PPSD or Z factor.
Thank you, Xavier. So we've got two more questions. So one question is about functionality. Can we study solubilizers like cyclodextrins? So the short answer to that is yes, we've been able to do that in the legacy version. So that's not specifically part of PPSD, but you can model cyclodextrins in the formulation with GastroPlus. The last question that is related to today's webinar is around, I think might need to go back to the slides to answer this question, if I understand it correctly, is can we select the particular particle size and see its effect on the PBPK as the formulation and not as the drug? So I think on one of your slides, you showed why the particle size of the drug may not be appropriate, and it's more appropriate for the formulation and hence the PPSD module.
Yeah, so you could input any particle size you want. As I said here in the observed data, you can decide that this particle size distribution is your granulate, for example, as an intermediate of your tablet, or you could use a PPSD based on dissolution, or you could use the drug substance particle size. It's all with the Johnson model. It's all going to be treated the same way. So you'll have a shrinking particle dissolving as a function of time, depending on the solubility in your GI tract compartment and the transit time, etc. So all the mechanistic of dissolution behind is exactly the same. The advantage of those I would say mechanistic model is when you run virtual BE. And when you have in your simulation setting, you select, the variability within subject physiologic within subject variability, then your in vivo dissolution will change for each occurrence of the dosing. So you'll reap the benefits of that mechanistic approach by having the right input. But of course, you need to validate it against your clinical data. So the validation part is generating sufficient number of variants to have different particle size distributions and verifying that you have a good prediction of the PK, like we did today in our assessment, really.
Thank you. Excellent.
Yeah.
So that brings us very nicely to time, and we've answered, or you've answered, well done, all of the questions that have been posed. So I'll hand it over to Heather, Jasmine, to kind of wrap up for today. And thank you on behalf of myself and Xavier.
Thank you.
Thank you all. So those that asked to be contacted for follow-up, someone from BD will reach out to you following the webinar. We invite you to visit our website to learn more about PBPK modeling and our other software platforms. I put a couple links in the chat if you also want to follow us on social media. This webinar has been recorded for playback and will be available on our website and YouTube channel. This concludes our webinar for today. Thank you, everyone.
Thank you. Bye-bye.
Goodbye.